I want to thank ILSI for giving me this opportunity to talk about something that I've had an interest in for about 15 to 20 years. But before I start, just let me tell you an antidote of what happened probably 35 years ago. There was a man named Ben Oser who used to be a toxicologist, pathologist, who was a very knowledgeable scientist, who wrote a book. And that book was, as it says here, Man is Not a Big Rat. The interesting thing, when I came home and I told my wife about this, what turned out to be a book, she said, no, it's not titled correctly. It should be Man with Few Exceptions is Not a Rat. So, under those circumstances, you may wonder if I question the use of rats, and actually I don't. As a model, they're not great, and we'll start with that. Let's see. I have no conflicts of interest, and now there's the, oops. There's what I think. Okay, even though it's a good model for a liver and a kidney, we pretty much understand everything about the differences between a rat and a human with regard to the kidney. And yes, it's not a rat, but I like the picture. What is it? Does anyone know? Yes, you're right. Now, I'd like to talk to you about something that's not about the rat initially, but I would like to talk about the TTC and how it's evolving over time and what's happened to it. As you know, TTC and the Kramer decision tree are currently used by JECFA, and they're currently used by the European Food Safety Authority in their evaluations of flavors. And they're used by the Japanese Food Safety Committee to do their evaluations. So it's reached the point where it has some practical meaning in terms of acceptability by regulatory authorities. And today I'd like to talk to you about how we're changing that tree and what's happened over the last 40 years, 50 years, and how the tree needs to change for its usefulness. How did it start? Well, it didn't start how most people think. Very few people understand the amount of time and effort that's gone into the tree. Initially, FDA, after the Food, Drug, and Cosmetic Act amendment of 1959, FDA started to study flavors. In fact, they committed a large budget between 1960 and 68 to the study of flavoring substances, safrole, eugenol, very commonly used materials. But they realized it was a hopeless effort because there were so many flavors. And they decided, well, why don't we work with FEMA on this? So FDA contracted with FEMA and worked with FEMA, the Flavor and Extract Manufacturers Association, to begin a process of taking 1,100 materials and reviewing all of the literature from 1900 to the present. And so in 1974, the process began, and the group that was interested or performed most of the work was a combination of chemists and toxicologists. But the toxicologist soon realized these were chemically identified material and they need to take the lead of the chemists. So the chemist sat down with them and said, we're going to read through these abstracts and these papers and we are going to organize these in a reasonable fashion to begin study. And they organized them into 69 chemical groups, as they called them. Compounds they knew were reactive in the same way and probably reactive the same way in the body. And these became the scientific literature reviews that they submitted to FDA in 1979, 1980. Those are available. Very few people access them, but they're available at the National Technical Information Service. And they're in the archives over in College Park. The thing that really astounds me is that this piece of work and the people who did it came up with the idea, why don't we write a tree, a sequence of questions which allows us to associate the toxicity of these substances in these 69 groups with the actual structure. And hence, Kramer decision tree was a combination of efforts of toxicologists and chemists to write a sequence of questions that would give you a classification of one of three classes, 1, 2, or 3. And if it didn't, it would send you on to another question until every substance was classified. And in the process, by 1978, they had published the article called the Kramer et al. Decision Tree. Now, it is 33 structure-based questions, well, mainly structure-based, and it allows you to assign any organic or metallo-organic chemical to one of 3 toxic classes, low, medium, high. And it was a good effort. One of the things that was absent, there was no information on the substances in terms of the toxicological and metabolic underpinnings of each question. That was never published. So the actual tree remained pretty much dormant for 20 years. But in 1995, Ian Monroe, University of Toronto professor and head of Health Canada for about 10 years, he decided, well, I'm going to associate each one of these classes with toxicity data and see if actually classes 1 and 2 and 3 have any toxicological difference. So what he was doing was studying relative toxicity of groups of substances, a fairly large group of substances. And this developed into something that became the decision tree combined with the JECFA evaluation of flavors and the threshold for the threshold of toxicological concern. God, I knew I'd get that out. TTC. Give everybody a break. So there's what it looks like. And as you can see, let's see if this works. What's that? Oh, wrong one. Okay, there we go. As you can see, can't see. I can't see. There. This is Noel's. So these are the Noel's we collected for about 600 substances. Here is the percent of data, or the percent of data that those Noel's were for. There we go. And you notice something, that there was a significant amount of overlap between the classes. They overlapped each other, and that was one of the complaints about using the tree. Well, don't these particular classes overlap each other? Yes, they do, and that was to be resolved, and it was a point of, let's say, discussion at JECFA during the 1996 meeting.
Turn it off now. You've got to turn it off.
Okay. All right? So those 3 classes corresponded. He said, well, how are we going to determine a level of which something is safe in each one of those classes? So he picked the 5th percentile Noel, which meant any substance or all substances in the class, 95% of them would have a Noel higher than the threshold. So that was a safe sort of concern and a safe level. And he picked that. Someone suggested 97, but there wasn't enough data to support that at the time. And so 95% became, a 5% threshold became the level that they chose as the TTC, which corresponded to each class of 90 micrograms for 3, 544 micrograms for level 2, and 1,800 micrograms for level 1. Well, there was a lot of criticism over the next 15 years. There was multiple publications on suggestions for improvement in the tree. One were isolated suggestions for changing particular questions to improve them. Others were questions on whether or not terms should be used like terpene, which is a really difficult term for a lot of people to understand, and also to a question like steric. What does that mean when you ask a question? Does it have steric hindrance? That's a very vague question. You need to give it structure. You need it to be a completely structure-based tree, and many people said that. But no one was willing to undertake the effort to do that. So we thought about it for a while and said, the only way this is going to work is we bring the literature up to date. We collect all of the information we can on metabolism and toxicity for the broadest range of substances that occur in food, which meant we'd started 15 years earlier. That meant it started 15 years ago. And it's been long in the process, and it's coming to the end, thank God. One of the, as you can see, some of the suggestions that were made was to update the 33 questions, to revise them, to make them completely depend on structure, and not any other vague term or question. By the way, there were questions in the old tree, is it a common component of food? Well, that's certainly not a structure question. So there were lots of questions in there that demanded judgment or demanded a library of what components existed in food, which really isn't related to toxicity. Structure is related to toxicity. And so the move was made to begin this process. Improving the tree meant we were to go into it and even consider aspects of toxicology that had been recently, shall I say, in vogue. This species-species difference in metabolism, the species-species dependency of certain effects, such as alpha-2-euglobulin in the rat kidney, or the male mouse liver, and his problems with spontaneous occurrence of tumors in the background controls. So this was all part of a massive improvement in the tree. Here are the substances that we decided to include in the tree, not only flavors, but natural constituents, okay, such as limonene and fatty acid emulsifiers and such as that. Unavoidable but manageable substances formed from food processing, like PHAHs, that's polyheteroaromatic amines, which have a control factor on them. They only produce them now at less than 150 for 4 hours. That's to avoid the production of FIPS, MIQX, MIQ, which are known animal carcinogens. They also industrial contaminants such as acrylamide, naturally occurring substance, fumanicin, etc. And then looking at natural colors and emulsifiers. So essentially everything you could find in food, even pesticides and animal drug residues and packaging migrants. So that means we were opening up to elements such as phosphorus, elements such as chlorine, fluorine, etc. So we're enlarging the tree not only by new questions, bringing new science in, we were also discussing the addition of new elements and new molecules. This was a massive effort. In order to develop NOELs that were reasonable, we looked for studies. Now, most of our substances that we have in our database, which is greater than 3,000, came from about 40,000 articles being reviewed. And of those 40,000, we came down to 2,000 substances that had sufficient data on metabolism and toxicity that we could produce about 2,000 reasonable subjects for further study. We used very few 28-day studies, which were from 28 to 35 days, and we used a factor of 4 to convert them into a chronic exposure. Actually, JECFA and EFSA recommend a factor of 5. We used 3, which is the common one used for a 90-day study and converting it to a long term. And then we also made the conclusion that any of maternal or paternal toxicity or a NOEL would be, in a repro study, would use the regular duration factor. Not the effect on the offspring, but on the female toxicity in the female or the male. We also took in some single dose studies if they were in the same range as other structure-related materials. So if we had methyl trisulfide, dimethyl trisulfide, we didn't have any data for it except for a single NOEL, we would study an additional, we would take that data and compare it to that for something like dimethyl disulfide, which had data for it, both multiple dose as well as single dose. And if it is in the same range, we included it. There weren't too many of those. Actually, we also reviewed all the Monroe data because he hadn't differentiated between cancer endpoints and non-cancer endpoints. And as you know, the JECFA procedure is a non-cancer endpoint approach. And then we expanded the chemical space. We not only added new functional groups, but we added new elements. As I said, phosphorus, chlorine, bromine, fluorine, and even iodine. And we compared whatever we got in terms of NOELs, we compared it to what expert bodies or authoritative bodies actually did, what they recommended. And we used EPA's IRIS, we went to JECFA, we went to EFSA, the Japanese Food Agency. So we actually consulted all those sources to make sure that our NOEL was not out of line of what other authoritative bodies were doing. And we normally took the lowest NOEL. Sometimes we disagreed, but we made our best effort. Let's see what else I want to say. Okay, so here we go. How did we develop the questions? We reviewed the range of structural feature. We reviewed that for a chemical group. So we went through a bunch of ketones. We divided up ketones into gamma diketones and their precursors, alpha diketones and their precursors, beta diketones, because they all have different toxic endpoints in metabolic data. I pointed that out. Target endpoints for one, of course, the gamma diketones was neurological. The beta diketones, they were liver, and the alpha diketones, they were primarily the lung, but they were ones in which protein adduct formation was occurring. So we went through them, then we identified the dose-dependent metabolic pathways. So we followed a substance like something like methyleugenol, and we tracked it through the rat and the mouse, looked at what dose-dependent metabolism was, the amount of protein adducts forming, the amount of DNA adducts forming. All that work was done on one substance. And then we looked at it, and we said, okay, we're going to make up a question about this substance and its group of congeners. Excuse me, but my mouth is dry. So we also evaluated the effect of additional functional groups. So if you have a molecule that has nitrogen, let's say it has an amine on it, aromatic ring with amine and a nitro function, we looked at that and then looked at the addition of an OH or a COOH to it. So we actually tried to vary things for a sufficient number of substances so that we could tease out other questions. The design of the structure-based questions was consistent with metabolism and relative toxicity. That was another guideline we had. The toxicity for the group must be consistent in a range, and it must be consistent with the metabolic information that we had. So this was a rigorous process. That's why it started 15 years ago. Chemicals that were structurally, as an example here, they were structurally similar They were classified first by carbon skeleton, just as the old tree, aliphatic, aromatic, alicyclic, and heteroaromatic, with one or more functional groups. An example would be we start off with alpha-beta unsaturated aldehydes and related alcohols and esters, and I'll show you that in a minute. And the metabolism, that is the hydrolysis of the esters, and the oxidation to the acid where it was occurring, and also the reaction with glutathione, and how dominant that was in the history. By the way, something like 2-hexenal, which is called green leaf aldehyde, it reacts like this when it gets in the body. It reaches the portal blood. As soon as it's in the portal blood, before you see it at the liver, it's already converted to hexanoic acid, which is a short-chain fatty acid. So this idea about testing something like 2-hexenal for adduct formation in the liver, which we've already done, as science has already done, that has already been done and shown to form adducts. But what's the point? It never reaches the liver, not in the concentrations we needed, or even 10 times that. So it had to be practical. So the next was, what target organ? We had to have a common target organ. We couldn't be dealing with a group that had a different target. So let me show you one of these. Let's see, here it is. We talked about the alpha-beta unsaturated aldehydes, and we made up a question. It was 28K, so you can imagine how big this tree is going to be. Is the substance is it allyl-alcohol, acrolein, acrylic acid, or a corresponding ester? Because we know the metabolism of that particular compound and all its congeners. And if yes, it goes into class 3. By the way, ahead of time, there are 6 classes. There's not 3 classes anymore. All right? If no, you go to question 29, which asks if it's an alicyclic substance, whatever. But you move along this, either move along the chain or you classify. Here's some data. As you can see, if you consider allyl-isovalerate, that's been NTP, allyl-hexanoate, cyclohexanepropionate, allyl-acetate, allyl-alcohol, acrolein. Acrolein is the aldehyde related to a direct subsequent aldehyde related to allyl-alcohol. As you can see, there are the no effect levels and there are effect levels, and you can also see it in millimoles per kg. By the way, we don't believe in using milligrams per kg per day. That's history. You have to count number by number. You can't count weight, especially when you have compounds weighing 3,000 in the same database with a compound that weighs 50 milligrams per millimole. So it's something you have to get used to. All right, you notice the toxicity. The toxicity of the longer chain compounds are less. All right, they're less by a factor of about 10, but they're all in the same range. The most toxic ones are the short ones. Okay, you see I don't have acrylic acid there. Why don't I have acrylic acid there? Why didn't I put acrylic acid in it? That's the next oxidation product. There's a reason for that. Okay, does anybody have any idea what reason it would be for not including acrylic acid? Because it's not the metabolite. The metabolite of allyl alcohol happens to be the mercapturic acid metabolite. In fact, you get the corresponding mercapturate that's being excreted. So that's why we avoided acrylic acid in this particular group. We'd only put it in if it were a possible downstream metabolite. So this is our part of how we develop, how our mindset was in developing this. Then we went to give you an idea, let's look at the effect of backbone skeleton, the same backbone skeleton, these are furan rings, but different functional groups. As you can see, the importance of functional group is really key to the process. If you go from furan ring has very few metabolic options. The only thing happening to that is it oxidizes, it ring opens, and it becomes a very reactive ene-dial that forms an adduct with a protein, as most compounds do long before they ever hit DNA. This happens in the cytoplasm, has somewhere else, but DNA's, unless you're being transferred through the cell nucleus wall, you have to have reactivity with the protein. It's going to be there. It's going to be in the environment. It's one of the nucleophiles that these reactive electrophiles deal with. So that's one thing to consider. So that was very reactive. You see, it's fairly toxic, too. Toxicity level, 0.013 millimoles per kg. It's in class 4, by the way, in the decision tree. On the other hand, what happens when you go to furfuryl alcohol? You put an OH on there. OH becomes a reactive functional group and produces furoic acid, which gets conjugated with glycine and readily excreted in the urine. Look at the Noel difference between the two. You have 2 orders of magnitude there. So therefore, furfuryl alcohol is in a different group than furan. One's in 4, the other one's in, as you can see, 2. And then we have another molecule, it's furfuryl mercaptan. You take OH off of there and put sulfur on, guess what? Sulfur is so reactive, it takes dominance over everything else. So the relative reactivity of furfuryl mercaptan is that it gets rapidly S-oxidized, or in this case, first gets methylated, and the sulfur gets oxidized as a sulfide, and it gets excreted as the sulfoxide. And look at its toxicity. Oh my God, it's 0.026. And what's the end point? It's different. It causes hemolytic anemia. That's because the furan itself, the thiofuran, that furfuryl mercaptan, actually reacts with red blood cells. And then there's a redox process with it, and so you develop those types of downstream effects. 5 minutes? Oh, you mean 10 minutes. All right. The next one shows you the difference between the carbon skeleton with epoxides, and everybody's worried about epoxides. Actually take the data and look at it deeply. You'll find only the short chain ones, that is with less than 6 carbons, in rat and mouse data and dog data. It is pretty reactive and in fact reacts with protein at fairly low levels. As you see, the Noel is 1 × 10⁻⁴ millimoles per kg. That's in class 5. Also, you have polyepoxides at the bottom. That is so reactive because it has three epoxide rings that actually you get cross-linking. That is protein cross-linking with that molecule, which makes sense. And it is also very toxic. But the first one, that is, you have an epoxide with a long enough chain. What happens when you get a long enough carbon chain, a ring like an alicyclic ring? It finds CYP450 in the liver, finds places to hit it and put OH on there. As soon as the OH is on there, it gets conjugated and excreted. So it goes in class 3. So what we've done is we've teased this out. We're left with those vague questions in the old tree, and now we're talking about specific questions, even about classes like epoxides. There's one more. I'm going to rush through this one. There's the effect. Notice the parent molecule at the top, that's in 5. The one in the middle has an OH on it. It's in 3. And the one with the carboxylic acid on it is in 3. Now, you all know why that is. That's you put a polar functional group on a molecule, okay, it won't react as normal if it had none there, and it will be excreted as a conjugate, either a glycine conjugate in case of the acid or a glucuronic acid conjugate in case of the alcohol or phenol. The top molecule is pretty reactive because it undergoes nitrogen oxidation to form N-hydroxy compound. The N-hydroxy compound reacts immediately with blood cells in a redox process, and so it causes all sorts of hemolytic effects. So as you can see, there's a lot of science that goes on in this. The last one, look at what happens when we put a diethyl and an isopropyl group on that nitrogen. Remember, nitrogen undergoes N-oxidation, so you get the N-hydroxy, which is not a good thing. What happens in the first one? Oh my God, it's hemolytic. Well, you expect that because flavin monooxygenase, that's FMO, and CYP, one of the CYP enzyme nitrogen oxidation, and you get the hemolytic effect. You do with this next one, which is a dimethyl compound. It's just not big enough. But you get to ethyl and isopropyl, what happens? Totally changes, because those compounds don't allow those enzymes to get in close enough, and instead of undergoing N-oxidation, they block it. And they block it, and what happens, it para-hydroxylates. That is, hydroxylates here and here, and gets excreted. So you see, there's a level of sophistication that this has that nobody has ever dealt with. We're actually making relative toxicity an important factor in determining the overall scheme of things. And so that is going to be the basis of this tree. Here's one thing that's just on the side, but it simply shows you that compounds that cause alpha-2-euglobulin, nephropathy in male rats, is caused by compounds that are hydrocarbons and compounds that are ketones, because they all get to one place. They either oxidize to a hydroxy compound and then a glucuronic acid conjugate, or they reduce and go to the glucuronic acid conjugate. That glucuronic acid is the substance that is transmitted into the proximal tubule of the kidney and conjugates with a globulin called alpha-2-U produced only in the male rat. So we should throw all that data out, which we've done, and we're using what? The female. So here's the tree. Here's what it looks like now. We started originally with a Kramer decision tree, and it had it was originally 613 in Monroe's database. Ours is more than 1,900 substances. There's what the tree looks like. Now you're going to say, oh my God, this is absolutely. Each one of these questions is multi-part. Like 28K, well, 28 goes all the way to R. Right? But some people think it's a tree, but I see it as a sunfish with a dorsal fin on the spear.
It looks like praying mantis.
Yeah, finished.
You make it more edible?
Look, I had it as a tree. We formed a tree with it, but it didn't look right. It was lopsided to one side. And as you can see, the whole mentality of setting up a tree is the first part. All the questions have to do with organophosphates, and there's like 8 questions, organophosphates. There's questions on nitrogen and sulfur functional groups that are reactive. There's questions on natural toxins. You wouldn't believe how you can fashion questions about naturally occurring toxins. We don't catch them all, we don't pretend to, but we catch enough to begin a process where other scientists can contribute. And we have aryl and aliphatic hydrocarbons, so a lot of these pesticides are in there, but there's like, I think there's about 8 or 9 separate groupings for aliphatic and aliphatic hydrocarbons. So we prioritized it. When you put a halogen on a molecule, if you only put one halogen on cyclohexane, it's harmless. It's a really low toxicity, even in a rat. So there are questions there that tease out, based on structure, based on the number of them, that tease out different groups and give you different classifications. As you can see on the halogen one, it has 3, 5, or 6. So we don't go any lower than 3, but it's in 3, 5, or 6. So we've classified substances. Oh God, here she comes. I knew she would. Let me finish. Yeah, there's my second, but I've finished with, I didn't get to the packaging materials. But look at how it sets now, folks. Now it sets. I wish I had that thing. Oh, screw it. Look at the red lines. The red lines are 1, 2, and 3. Those are the old Monroes. Look how much they overlap. Look at the classification of 1, 2, 3, 4, 5, and 6. You see how well separated they are? And they only range about 2 orders of magnitude. So therefore, the difference between class 6 and class 1 are about 9 orders of magnitude. So we have the most toxic substances you can think in. Sarin's in here. Water hemlock's in here. There are compounds that the people spend a great deal of time and effort to get in OLs, and now nobody's put them to use. And we thought, let's put them to use. So we put them in there. And you know what it points out? If you look at the numbers for these, if you term the ETT, the TTCs for the new tree, now they take that old class 1 of Kramer and the TTC of 1800, and they have 2 TTCs, one of 22,000 and one of 4,000. And then class 2 is now double what it used to be, 988, and class 3, 4, and 5, well, one's above the 90 and 2 are below the 90 because those contain really toxic substances. And so it sets out what should have been done a long time ago. Somebody should have taken the data and updated the decision tree and seen that, my God, we just dumped too many compounds into one class. If you know the old tree, like 90% of the compounds were in class 3. Well, that wasn't a tree at all. I know, I worked on the original decision tree when I was at FEMA. So, if anything, this has a huge impact on how we move forward. Do we move forward with this type of data, which shows you here, you have the TTCs, the number of compounds, and you see what has happened to the percentage of compounds in class, what used to be class 3. It's now in class 4, there's 634. About 30% of the compounds are defaulting into that class. The rest of them have well-defined questions to place the substances in 1, 2, 3, 5, or 6. So we think it's a mass improvement, and we're trying to get the paper out as soon as possible. In fact, 2 papers. A concept paper that demonstrates our thinking, and then a paper on the actual tree itself, which you might imagine is going to be big. And we'll wait for the scientific community to make comments. And hopefully we'll get a few of them, hopefully many of them, that want to change the tree. Because there lies the strength. So